I'm making this tutorial for digital design 2 students, basically in electric and how to use electric with Ltspice. Let's start. Basically, in this tutorial, we're gonna build an inverter using electric. The first thing here, and this is electric, you will start by renaming our library to be like inverter or something, or yeah, inverter maybe. Uh, then we will start. I'd say that I'd like to make this pretty fast because all the tutorial in electric takes a lot of time and does not give the information. So inshallah, maybe this won't go beyond 15 minutes. Uh, I'll create a new cell and starting from the schematic. And yes, must type a cell name. We will name the cell IMV. Say OK. Now start here, and now we are in this schematic. We go to the components and start to add our components. The first thing is, in an inverter, we need a PMOS, we choose one and add it. We need an NMOS, choose one and add it, and connect the connection of an inverter. Like, I assume that you already know that. So, basically, we have we need a ground to connect to the signal here. So we choose ground from here and connect it directly to our NMOS, and we need a VDD to connect it to our PMOS. Okay. Now here we connect to the input. You know that we have in the inverter we have a common input and a common output. How do I assume that you don't know how, if you don't know how to make these connections, like to make this wiring, you just like click on any node, click on any active node like this on this place, then sorry, left click on this, then right click at anywhere it creates the wire. Like now I'm here highlighting this with my left click, and now right clicking on this, that connects the wire. As you know, an inverter has one input and one output, so the thing that indicates the inputs and outputs here um, in electric are exports. You create exports. So here we can say export and then create export and name our first export here, for example, in as for input to the inverter, and say okay. But now okay, it's not accepting this because we are does not have anything highlighted to connect the export to. So we highlight the point that we connect the export to, then we say create export and name it, for example, in, and say okay. So why are we creating exports? Basically, after you create this module, you're gonna simulate it or something, or use it, you will use the names of these exports in simulation. Here, as we created it, we can create export using Control E. So it makes the same thing. You just click on the place that you would make an export from and press Control E. And let's name this export out. Okay, so now we have in and out. Here, as you see, the transistor, the NMOS transistor, it has like two parameters that you can set, and it has actually more than those two parameters, things related to the position and the rotation. I think just the rotation, you can use Control J and press Control J when you are selecting the item, and it would rotate 90 degrees. Here you can specify the name. You specify the width and the length according to the design rules that you have. Like if you need the PMOS to have a greater width than the NMOS, which is the case in order to have an equal delay for rising and falling signals, for example. So you could change it easily from here. And that's it. And also for the PMOS, you have the same parameters here, and you can expand it to see all these parameters. Okay, so let's go back to our Explorer. We have here the inverter schematic. We create for this inverter schematic what is known as icon view. The icon view for the inverter schematic is basically a thing like this, which you can edit Okay, to use, sorry, I can just Control J this or something. Yes. Okay, that's relative. Yes. Sorry. So basically, I'll edit this. The icon view gives you the ability to, for example, if you want to change to reduce this inverter to only like this shape, so that you have only access to the inputs and outputs, and you don't have to deal with all of this shape, especially if you're gonna make like complicated simulation. Or for example, here you could just play with this thing, like you can add different components, make the shape of the inverter as you please. So we could move this right here and make it more look like an inverter. Yes, and this now is the icon that we could use instead of using this whole shape in our simulation. After that, I'll show you how to do the simulation. But first, before doing any simulations, let's transfer this from the schematic view and start to build its layout view. To build the layout, basically, we get here or here, like it never like makes a difference, and we choose the name as inverter, the same as the name of the schematic, and we choose layout. Okay, let's press OK. Now we have a layout, but before start working on the layout, we have to I forgot about this, I should have said that in the beginning, but like let's make the configuration for our design. So we go to File and we go to Preferences. In Preferences here, we should configure our project. So what are the design rules that we are working with? The technology. The technology is likely to be the most important parameter that we're gonna set. Here, our scale, we go to this mock mouse. I don't really know what are the different choices are, but what I know that mockmos here represents lambda. So you enter here lambda, okay, of your design. If you want, our technology is mockmos. We are working here with only 3 metal layers. If the doctor told you, yeah, like if you have in the file thing that says that you're working with the different technology, with the different scale, everything could be changed from here. Here is the input to the lambda, as lambda is the most important parameter in this. Okay, so that's basically the setup that we need, lambda. Now let's start to working on the layout. In the layout, if you see here, when we are in the schematic, the components are in the schematic, the components are schematic components. But when we go to the layout view, the components now are components that could be used in the layout. Here we have NMOS, PMOS, we have P wheels, N wheels, P active and N active, and we understand what each one of those do. So basically, for digital design tool, you're gonna need to like build or nor cell or something. So we are just playing here with the simple one, which is the inverter. So for an inverter, we need an NMOS. We will just place the NMOS here. Okay, let's go here and see that in our schematic we place the NMOS down and the PMOS up, just for the sake of being for regularity. We'll go with that. So sorry, have here, as you can see, NMOS. We'll rotate it. Okay, NMOS components. We add our PMOS and rotate it. basically, as you can see, I don't really know, but like here we need to follow the DRC rules. As you can see, these dotted lines say or indicate the territories for different components and the clearance between different components. Let's keep them apart. I when I work with electric, I keep the things apart because it results in DRCs until like adding all the components to the PMOS up here, then adding all the components to the NMOS down here, and then start to get them closer because until we have like we are the closest, but we don't have the RC errors at the same time. So the first thing we have here the NMOS, we will go and get inactive. The inactive enables us to connect the NMOS to metal layers. So we connect the NMOS here with inactive and the PMOS here with P active. Here we add the P active. Okay. We start by putting them away, then because I don't know really, electric produces some strange DRC errors sometimes, but doing it this way might grant you that he's not gonna produce some strange error messages. So as we were connecting the connections in the layout view here in the schematic view, we left click on what we want to connect. Then we right click on the other side, and then we have a connection here. Same goes for here. Okay. Then I start to, by the right arrow, by pressing the right arrow or the left arrows or using the arrows, I start to get this closer and closer to our transistor, to our here. As I said, we start to get this closer and closer to the transistor, and at each time we run an DRC to check if there are any DRCs at this area. Now we have, it says here that we have 3 errors. So, and we use shift plus, like greater than, shift plus less than, to traverse through the errors. So here all of the errors are up there and the unconnected stuff. So we continue to get this closer and closer and run F5, 3 errors, the same 3 errors as before, closer and closer, and run F5, the same 3 errors, get this closer. Okay, so make this symmetric. You know that we need here to make the width a multiple of sites according to the project that you're asked to do or something. You can make this multiple, like the site is equal to whatever width, to 2 lambdas, 3 lambdas, 4 lambdas or something. Then make this multiple of that site. Here we connect those and start doing the same thing, making it closer and closer until you have no DRC errors. Okay, function F5 checking. So now we have no DRC errors either here or here because they are connected, and we are ready to start working on this. Okay, so we connect the inputs and the outputs. As you know, the inverter here, we try to get this closer and closer to the other one because as you know, when you are like making a standard cell library, it's better to have a lower height for all the cells. So we try our best to make this compact, as lower height indicates that uh, we could better use our space. So we make it until we don't see a GRC. I think it happens when these areas are not intersecting. Now after that, the red stripes here are the places that we are at which we are making the connections. So we're pressing here a left click and a right click here because we know, as in the schematic, we're connecting here the I think it's not called the base for MOSFETs. MOSFET. Okay, I don't remember really. Most it's so here we have the gate. The input is connected to both the gates of the PMOS and the NMOS. So in the layout, we connect this is the gate of the transistor. We connect the gate of the NMOS and the PMOS together, and then we take this drive and here create an export, Control E. Also, this export is used for simulation purposes. We name this export after this export. So this is named in and this is named out. So we here name this in because it's the same export in the schematic, and the naming is important to be similar between the schematic and the layout, because after this we are going to perform a layout versus a schematic or LVS test, and the LVS test brings errors when the names are different. It literally compares the schematic with the layout and ensures that the both match. Now we have connected, as in the schematic, this phase. Now we need to collect two terminals at this one, two terminals of the transistors to the output, and in doing so we use the metal layer 1 metal. So we press here, left click, right click, so those now are connected, and press on the metal and create an export for the metal again and name it out after the export name in the layout. Sorry, in the schematic. Now, here, we need to connect the other two terminals. Those are the other two terminals of the two transistors. The PMOS have to be connected to VDD, and the NMOS have to be connected to ground. And in doing so, we need we cannot directly connect like VDD and ground to the transistor. That's because we need something. There was something called tapping or something. Tapping where we add with the NMOS we add PWL in order to perform that tapping. Okay, I don't remember really the physics behind this one, but we add a PWL uh, for the NMOS to connect the ground to the NMOS, and we add an NWL for the PMOS to connect the VDD to the PMOS. Okay, so here we have our PWL. We specify its X size to be wider than this, maybe go for 20 or something. Say okay, we move it here. We check if there's a DRC or something, get it closer, check the DRCs. No DRC is closer than this, it will produce in DRC. It's just like the yellow areas. The yellow areas, if you can see these yellow areas. Now after this, we connect this one with this one as usual. Right click, left click. Now we have this connected. Sorry, this. What is this? This is the MOS connected to a PWL. Now this PWL, we create an export for the PWL, and this export, name it ground. It's like a generic name for ground. Sorry. Move it right here. And we go here, as we made a PWL here, we will add an NWL, open its settings, make its X size equal to 20. We make this X size according to the site size, or we have two sites for this cell or 4 sites. Multiply this by the site size. Okay. Now move this until no DRCers shows. That's okay. Now we have this, and we create an export for this and name it VDD. And VDD is also a generic name for our VDD. And in the simulation, we could specify this VDD to be like 3.3 or 5 volts according to the operating voltage of this cell that we will decide on. Now we have our cell ready. We are running F5 DRC. We have 0 errors and 0 warnings. Now we will run an LVS or layout versus a schematic test. Simply we press J sorry, Control J. Sorry, it's LL. So so we have ran after finishing this. Okay, after finishing this, we run a DRC test and we have here 0 errors and 0 warnings. Now let's run the second test, which is an LVS test, which is a layout, this one that we've just made versus a schematic test. And we can run this simply by pressing L. And by pressing L here, he shows like errors, and we check this, and he says something about the sizes. We have error in the sizes. Width is 2 for an NMOS named NMOS0 and the cell inverter.env, and the width is 3 for the same cell named NMOS P0 in inverter.env. So now in the schematic and the layout, we have here, if we check the width of uh, this transistor, double click it and check the width, we see that the width is 3. So and if we go to the schematic and check here the width, we will see that it's 2. Okay, so this is a contradiction between both the schematic and the layout. So we have to change one of them to match the other. Here we will change this into 3 because in our design rules, it's not allowed for this transistor or that transistor to have a width less than 3. So we changed the schematic. This is 3, and also you'll find that this is 2. So change that width into 3. Now we go again to the layout and press L. And now, as you can see here, summary for all cells, exports match. We have here exports out and in, and VDD and ground. All of those 4 match the same in and out, and the export here and the export there. They are all matching. Okay, topologies match and sizes match. So everything is correct. Topologies, I think it's about the connections, because if you make a wrong connection, he will tell you that you are not connecting the MOSFET in the right way, and the sizes match. So all good now. Let's go for the last step, which is simulation. Now we have created our schematic and layout. Let's make a simulation. We'll just go here and create cell, new cell. It's a schematic cell, and name it msim or something. So okay, and msim here, we will drag our icon and put it here. Okay, we can drag the schematic itself. But as you can see, it's not that beautiful, so we could use the icon, and also we could you could drag the layout and simulate the layout itself. Let's now take an example and simulate the icon, which is technically simulating the schematic. The simulator that we are using. Oh, first, okay, so here it's like it's a symbol for inverters, so we have to make exports, making exports for these symbols. So here we go Control E and name the export according to the name that we will give it in the SPICE simulation. As you know, we're gonna perform a SPICE simulation on this. So for example, let's name it A. Okay, and here create another export and name it out, and it's case sensitive, so you have to care about this. We're naming this out, and we are naming this A. Okay, now if you didn't do that before, the setup of the simulator with electric, we are using Ltspice for simulation. So basically go to preferences here, and we go to tools, we go to simulators, I think. No, Spice, yes, Spice CDL, which is here. Choose the Spice engine to be Spice 3, Spice level to be 3. You can just copy all the different parameters and check if something's different in your configurations. And here we give him the path for this, the place where we have set up Ltspice, so we could run the file. Okay, now we have to write the spice dict. writing the spice dict. How can we write the spice dict? Simulation spice. Sorry. Uh, let's continue our discussion about the spice. So to write the spice code for this, we go for components when we are here in our Explorer in the MSIM module. Go to our components and go to miscellaneous and choose from here spice code and put it here like that. Now we have a text. That text or that spice code, you shall in order to like write your own code, you shall consult the spice files that were sent to you by the doctor. I can send you those if you want. Just like type your email somewhere in the comments or something. Okay, so here we're gonna go and open electric again. We will open one of the past project for a simulation for an inverter. Open library, not the tutorial, project one, inverter, inverter.glib. Okay, now we have here the simulation, and this is the code. I'll explain this code in a minute. We'll copy it and we'll go to here, and in our code here, we'll just first okay, Control I. So in order to edit this, in order to edit the settings of anything, you can just select it and press Control I. Here we will make this spice code a multi-line text, and we will pass here the code that we extracted from there. So press OK. What does this spice code do? Basically, let's open this. We are defining a VDD. Okay, we are defining the values of the VDD and defining it between 0 and 5. And the syntax itself, you can consult the syntax the Spice files, so on how to write Spice code that the doctor sent you. So we have VDD from 0 to 5. You can change this value of 5 to 3 volts or 3.3 if you are working with 3.3 voltage or something. Okay, so then we define VA. So this name is put after a small v, then it's repeated again. That's the syntax. Okay. 0, DC 0, these are values that you can consult again. And the spice code thing. We produce a pulse. Okay. That pulse is from 0 to 5 and specifying the timing of the rising and the timing of the fall, and this specifies the full time of simulation. Okay, now here you could have been asked to calculate the CM or something. You assign to the output, okay, C load. So out here is written as it's written here exactly with all uppercase letters. Okay, and setting it to 150 femtofarad. You can change these values as you wish. Then we put here two statements, directive statements for the simulator, okay, to measure the rise, the T propagation delay of rise, and it's triggered on V out, uh, uh, starting at 0 and measuring the time until we reach 2.5. Okay, and here we are measuring the full time. So we see that here full equals 1 and here rise is equal to 1. Run the simulation for 15 nanoseconds or something. I don't remember the meaning of this one. Then that one. This is one of the most important things, that to include the MOSFET model that we're gonna use. Here is an important thing. If you go here and do the schematic, here in the schematic view, we have to set the spice model for this transistor, for example. So this transistor, the spice model, how to set that? We go to Tools, Simulation, Spice, Set Spice Model, and then now we name the spice model N, for example. And where do we get the name from? I see that the doctor have sent you a spice model. The doctor in the previous semester sent us one here in sorry, project one, I think inverter, and we go to MOS text here. So this is a spice model. You don't write the spice model, you just use it. So here in the model we have two components, an N component which refers to the NMOS, and a P component which refers to the PMOS. So basically here in our project we set the spice model of sorry, that's the PMOS. So we set the spice model of the PMOS to P, and here also we go to here and set a spice model to be N. Okay, so now we have P and N. So when you are simulating here, when this code go to the simulator, go to Ltspice, it basically goes to this path and extracts the model and feed it to Ltspice, and then he could understand how these MOSFETs work, so that he could give you a timing analysis, a good timing analysis of that. Now we save our project. We could save it here in tutorial. Okay, name it like this, overwrite, no problem. Now we have a saved project. After we save our project, we go to Tools, Simulation Spice, Write Spice Deck. Here, after writing the Spice Deck, you should have already linked Ltspice with electric, so that after saving this, it will directly run electric. Here in electric, you could view the input that we could call VA and the output that we call Vout. Press OK. As you see here, it's working like an inverter. If you zoom in, you could see the step response and how the delay in the output is different. Okay. Now we go and see after running this, after running the simulation. Okay. Beside the project files here, you will find a new file named invertersim.log is produced. And this one, you'd find here time propagation delay of rise have been recorded from the starting point to the ending point, and time propagation delay of fall also has been recorded. You could use these together. Sorry. Could use these together with the value of the capacitance that you have set here to calculate different values that you might need, like the CM or something. That's basically it. That's how to use electric and how to use Ltspice with electric. I hope that was beneficial for you, and thank you.